So let's start today's tutorial with the topic computer organization and architecture. So let's understand what computer is basically is. So computer, as we all know, is a device which processes the input and gives our desired output. So basically, it is a processing device. So we give a data. So basically, what data is? Data is basically a set of instructions that is given to the computer. So it is, suppose, the computer. So we give data to the computer, and data is basically a set of instructions, and the computer, it processes the data and gives the output. So before going into the aspects of the architecture of the computer, we are going to see what a computer basically understands. So we human beings understand the language like English, French, German, or any other language. It is understood by us, but the computer, on the other hand, cannot interpret those languages spoken by human beings. So it can only understand some basic logical operations such as multiplication, subtraction, addition, and all the processing is done in the form of binary. So it basically understands binary. So what basically binary is? It is combination of zeros or ones. So a computer basically understands the data in the form of binary, but we cannot directly give the instructions in binary format. So uh, it will be a very cumbersome task for us to write the data in binary form. So we basically use any languages such as C or C++ or Java. So basically, these are some of the languages that we use to make the set of instructions, that is the data, and the compiler. So the role of the compiler here is to compile this set of instructions in the form of binary, and the computer processes it and gives us the desired output. So basically there are three types of languages. One is high level language, the other one is low level language or the machine language, and one more category of language is the middle language. So the middle language is very near to the machine language. So the examples of high level languages are C++, Java, C sharp, and the machine language is basically the binary zeros and ones that a machine basically understands. And the middle languages, example of the middleware languages are C. So C is basically neither high level language or machine language. It is it So a data can be a set of instructions, a video, a photograph, or anything, but the computer processes the data in the format of binary. The voice the voice is compiled into digital signal by some softwares, and this is the basic organization of a computer. So in this tutorial, what we are going to see is the language of bits. So we are basically talking about the language that a computer understands. So a computer can only understand the language of bits. So this is true. Now, what is a bit? So a bit only contains 0 or 1. And there is one more term, that is a byte. A byte, uh, the size of byte is 8 bits. And as we move forward, we have one more category, that is word. So a word has 4 bytes. And then we have a KB, kilobyte, that has 1024 bytes. And then we have MB, which stands for megabyte, which has 1024 kilobytes. So yeah, so the computer understands uh, these inputs, which is in the format of 0 and 1s. So let's move forward and see one more concept, that is a truth table. So we are going to deal with the following operations in a truth table. The first one is OR, second one is AND, the third one is NAND, fourth one is exclusive of OR, and we are going to look one more, that is NOR. So let's see what a truth table is. So basically, a computer understands inputs that contain only the binary digits. So let's take A to be 0 and B to be 0. So we have in OR operation, we say A or B. So A or B is basically A plus B. So 0 plus 0 is basically 0. So A or B is 0. If A is 0 and B is 0, then A or B is 0. If we take A to be 1 and B to be 1, then A or B is again 1, because A plus B, so we are not adding it, but we are just um, we are just we are just seeing that if the output is um, we are just seeing the output if the output comes to be any number. So in case of OR, if we are getting any output besides 0, then we have to give that 1 instead of 0. So yeah, so if we are having here 0 and 1, then A or B becomes 1. And if I give here 1 and here 0, then also we are getting 1. So this is the truth table of OR. Now let's see the second one, that is and. So if I am telling you that I have a0 and b1 and 1 0 1 1 0 0. So a and b basically means a into b. So this is a into b is 0, this is again 0, this is 1 and this is 0. So if both are 0, then we are getting 0. If either of them is 0 or and the another one is 1, then we are getting 0. But if both of them are 1, then we are writing here 1. So this is basically the AND operation. Let's see the third type, that is NAND. So NAND is nothing but it is complement of AND. So uh, let's see this slide. So so the complement of any so the complement of any uh, digit like 0 is 1 and the complement of 1 is again 0. So if I am writing here a, the complement of a is suppose I am taking a to be 0, then the complement of a is 1, and if I am taking a to be 1, then its complement is 0. But if I take double complement, then it becomes a only. So this was basically about complement. So in this case only, uh, in this case also, if I'm taking the NAND operation, then the NAND of uh, this operation, we just erase it. Okay, so the NAND operation. So NAND of this A and B is 1. So the complement of this only. The complement of 0 is 1. The complement of 1 is 0, and the complement of 0 is 1. So this was about the NAND. The next operation is NOR. So NOR is basically complement of OR. So what you have to do is basically um, we have the OR gate. Let me just erase it. Now let me A NOR B. In this case we are taking complement of OR. So the complement of OR here is 1. The complement here is 0. This is 0. This is 0. So this was basically about NAND and NOR. The fifth one is XOR, which is exclusive of OR. Exclusive of OR. We can write XOR as this: A XOR B. And this basically means let's make a truth table of XOR to understand this. So I am having A, B, and A XOR B. So if I am having A to be 1 and B to be 0, A 0, 1, 0, 0, 1, 1. So the XOR of this thing will be 1. The XOR of this one will be 1. The XOR of this one will be 0, and this one will be 0. So the basic concept of this XOR is uh, whenever we see the same entities, then uh, we have to make the operation result to be 0. And if we are having different entities over here, then we have to uh, give the XOR operation to be 1. So I have 1 1, then I am writing here 0. If I am having 0 0, then also I am writing 0. But if I am having different entities, then I am writing here 1. So this was basically about the XOR. And Let's see some of the operations. So the first operation is the complement of 0 is 1 and the complement of 1 is 0. Second one, the double complement is a of a is a, as I said previously. Then a plus 0 is a, so this is basically a or 0, so this is basically a. And then a times 1 is a plus 1 is 1, a minus, okay, so a into 0, a into 0 is 0. So this was about some of the operations that we can perform. This will be useful, and we are having some of the rules. The first rule is independence rule. So it says a plus a is a, and note that the value of a can be either 0 or 1. So if I am having a to be 0, then 0 or 0 is basically 0, and 1 or 1 is basically 1. Okay, now the second one is a times a is a, so this is a and a is a. So if I am having 0 and 0, then I am having 0. So if a is 0, 0 and 0 is 0, 1 and 1 is 1. The second one is complementarity. So this says a plus a complement is 1. You can see that if I am taking a to be 1, then 1 plus 0 is 1. And if I am taking a to be 0, then 0 plus 1 is again 1. Also note that a times a complement is 0. If I am taking a to be 1, then its complement is 0. Then a 1 times 0 is 0. The next one is commutative rule. So the commutative rule says that a plus b is equal to b plus a, and a times b is equal to b times a. Next rule is associativity. So associativity says a plus b plus c is equal to a plus b plus c, and a times b minus a times b times c is equal to a times b into c. So this is the associativity rule that we can apply. Now the next rule is distributive rule. So the distributive rule says that a plus b plus c is equal to a times, so the distributive rule says a times b plus c is equal to a b plus a c, and a plus b into c is equal to a plus b into a plus c. So these were some of the rules that will be very much helpful while doing any operations. Uh, let's see one more law. This law is De Morgan's law. So the De Morgan's law says a plus b is equal to a into b. So a plus complementary of a plus b is equal to complementary of a times complementary of b, and a time complementary of a times b is equal to complementary of a plus complementary of b. So this is De Morgan's law. You can prove these two. uh, let's take a to be 0 and b to be 1. Then a plus b complement uh, from the LHS, a plus b complement is basically 1 complement, that is 0, and a complement is basically 1, and b complement is basically 0, and a complement times b complement is equal to again 0. So LHS becomes equal to RHS. Hence first one is proved, and you can prove the second one in the similar manner. So let's move forward. So let's do one question related to this concept. So we have one theorem that is also known as consensus theorem. So the theorem is x times y plus complementary of x times z plus y times z is equal to x times y plus complementary of x times z. So this is consensus theorem, and we are not interested in this theorem, but we have to prove this theorem. So pause the video and then try to prove by taking LHS and try to make it equal to RHS. So you can pause the video now. Let me take LHS to be x times y plus complementary of x times z plus y into z. Now if I write here 1, there is no issue in this. Now let me write here x times y plus x times z plus y times z. Now 1 to be x plus x complementary of x. So x plus complementary of x, if given x is 0, then 0 plus 1 is 1, and if given x to be 1, then 1 plus complementary of x, that is 0, is again 1. So we can write 1 to be x plus complementary of x. Now let's write here xy plus y z x plus x bar z plus y z x bar. Now taking out common xy, we have 1 plus z plus taking out common x bar z, we have 1 plus y. Now the value of 1 plus z is 1, so we are left with this thing, which is equal to RHS. Now how this is 1? Because if we take z to be 0, then 0 plus 1 is 1, and if we take z to be 1, then uh, if uh, if we are having a to be 1 and z to be 0, then a plus b, that is a or b, is 1, and if we are taking, we write it here z. So if we are taking z to be 1, and this is, if we are taking z to be 1, and we are all, actually having the value of b, that is 1. So z plus b, that is z plus 1, is basically 1, and if we are taking z to be 0 and b is actually 1 only, then z plus 1 is again 1, because this is OR operation. This is nothing but OR operation. So the value of this becomes 1, and in the similar way the value of this also becomes 1. So we are getting LHS is equal to RHS. So this was the proof of this theorem.